Okay, so for the next chapter, we want to start talking about temperature and heat. Okay, temperature and heat. And we're going to give both of these a bit more of a rigorous definition than probably what we use in our colloquial language. But let's first start talking about our temperature scales. Temperature scales. Because we need to have a system with which we can differentiate between different types of temperatures and different temperature ranges. And the scale that we're probably most familiar with here in the United States would be the Fahrenheit system. I never can spell it, so I'm not going to try to. And there's another system that is often in use, and sometimes they use it in other countries, in doctors' offices and things, and it's the Celsius system. In science, though, it's often best to use what we call the Kelvin system. Okay? And notice that I didn't put a degree sign here, okay, because technically an object that is measured, has its temperature measured in the Kelvin scale, the Kelvin unit is actually, in fact, unitless. So there is no such thing as degrees Kelvin. Okay, we would just say the number and then Kelvin. All right, but the Fahrenheit and Celsius scales have two similarities in common, even though they have different actual scales that they use. The 2 points that both of these have in common are the freezing point of water and the boiling point of water. So it is this, or I should say these two properties, that anchor these two scales, whereas the anchor for the Kelvin scale is absolute zero. Okay, and you'll see what I mean by that here in just a minute. So Fahrenheit, for the Fahrenheit scale, we say that 32 degrees Fahrenheit is the freezing point of water, H2O, and 212 is the boiling point. Of H2O. Whereas for degrees Celsius, we have 0 degrees as the freezing and 100 degrees as the boiling. And this probably makes more intuitive sense to you than the Fahrenheit, although the Fahrenheit's probably more, you're more accustomed to the Fahrenheit. To me, this system simply just makes sense. If we're going to use water as our anchor, why not call the freezing point of water 0 and the boiling point 100? And it's a very nice and simple scale. There's only 100 degrees difference between the two, whereas there's 180 degrees difference between the two in the Fahrenheit system. But how do we convert back and forth between these two? Well, the two formulas, if I know what I have in Fahrenheit, I can calculate Celsius very quickly. So I can calculate my degrees Celsius very quickly if I know what my temperature is in Fahrenheit by this formula. And I'm sorry, actually, this one should be a minus. The other formula gets a plus. So if I know what my temperature is in Fahrenheit, I subtract 32 from that number and then multiply by 5/9, and that will give me my value in Celsius. Now you may be wondering, where does this 5/9 come from? And it comes from the fact that, as I said before, between freezing and boiling, the Fahrenheit system has 180 degrees, whereas the Celsius system only has 100. So if I'm converting from Celsius to Fahrenheit, I need to take a factor of 100 over 180, and that boils down to 5/9. Whereas if I'm converting from Celsius back to Fahrenheit, I'm going to have a factor of 180 over 100, which will give me 9/5. And so that kind of leads us to how to convert. If we know our Celsius, how do we convert back to Fahrenheit? And so the formula for that is going to be very similar to the one that we've already written down, but it will have its difference. And one might be tempted to say, well, if I know what my degrees are in Celsius, I can just reverse this operation and say 9/5 times my degrees Celsius plus 32, and you would be close to being right, right? But this formula is not quite right, and you'll see why in a second. And that is, if I want to solve this formula for Fahrenheit, then I first have to undo the 9/5, or the 5/9 rather. I first have to undo the 5/9. And so what I need to do is take my Celsius and multiply it by 9/5, and then add this 32. Okay? So I do this operation first, and then I add the 32, as opposed to adding the 32 and then multiply by 9/5. Okay? So this is how you can go between both temperature scales. And the issue with the Kelvin scale is this, okay? The issue with the Kelvin scale is this. Imagine that I have three gases, gas A, B, and C, and I look at those gases, and I let my x-axis here be temperature, and I let this be 0 degrees, okay, and this axis will be pressure. As I look at different gases, I change the pressure inside each gas and then take a temperature measurement. I might get something like this. And I get a trend line that runs back this way. And I should probably extend this backwards some. Okay. So my trend line hits my x-axis right here. And then if I have another gas and I look at its pressure and temperature as I vary the temperature, its graph would look something like this. But it would essentially come down to the same point. And then one final gas might look something like this. It'll also have a trend to it, but it will also come down and meet in this exact spot. And we call this point, notice I'm now at a negative temperature, so I have negative temperatures here, I have positive temperatures on this side, and they all meet, all three of these trend lines meet down at this specific point. We call that point where the pressure goes to 0, we call the temperature where the pressure goes to absolutely zero, we call that absolute zero. Okay? And that happens to be at negative 273 Kelvin. Okay? So it's called absolute zero because that's where the gas ceases to have any pressure whatsoever, or at least these models predict that the pressure goes to zero at that temperature. So the Kelvin scale is anchored at negative 273 Kelvin. Now, 0 Celsius is 273 Kelvin. Okay? And the temperature increments on the two scales are the same. So 1 degree Celsius would be 274 Kelvin, and 20 degrees Celsius would be 294 Kelvin, so on and so forth. And so the temperature increments are the exact same. All right. Now we need to talk about one specific topic called the heat capacity. And we'll use this term to describe whether or not, we will actually use this term to give a more rigorous definition to the term temperature, if you will. So, heat capacity is essentially the quantity or the amount of heat needed to change the temperature of an object. And we can now define something even more specific, and we will call this the specific heat capacity. And the specific heat capacity has a bit of a longer definition, but it is essentially the quantity of heat needed to change a unit mass of material by a unit amount in temperature and your book gives the example. It would be, for example, the amount of heat needed to change the temperature of an object that was 1 gram by a temperature of 1 degree Celsius. Okay. And it is a property of a material. So each individual substance has its own heat capacity, or its own specific heat capacity. And we denote the specific heat capacity by the letter C. All right. And so if we come back here, it's the quantity of heat needed to change a unit mass of material by a unit amount in temperature. So it's the amount of heat that I would need to give to an object to raise its temperature by, say, 1 degree per 1 gram of its substance. Okay. Now we denote heat, actually I should come back here, we denote heat by the letter capital Q. Okay. So Q is heat. So the total heat given to an object, we can find the total heat given to an object is going to be equal to its mass times its specific heat capacity times its change in temperature. Okay? So if I have a substance at a low temperature and it has some sort of mass and I know what its specific heat is, I can determine what temperature change it will experience, or I can also, well, let me finish that thought. I can determine its temperature change, or what temperature change it should experience given an amount of heat that I give it, or if I measure its temperature change, I therefore then know how much heat I have given it. Okay? And your book has some sample heat capacities for a few given substances. But this now kind of allows us, that we've introduced this term heat, to define exactly what heat is and exactly what temperature is. And once we do so, then we will do an example with this particular equation and let you see how it works. So, heat, okay, heat we define as the energy flow from one object to another when there's a temperature difference between the two objects. Okay, so that's the idea of heat. Temperature, on the other hand, we define as the quantity that indicates whether or not and in what direction heat will flow. Okay? So really, the idea of temperature is almost relative to a second object. Okay, so the idea of temperature itself, you almost have to take something's temperature and then compare it to something else for the actual measurement to make any sense. But here's a rule for heat. Okay, let's go back one slide here. One rule for heat: it will always flow from a hot object to cold object. And we'll actually see why that is. If not this chapter, then the next chapter, we'll actually see why that is. But at its the base of this statement, what it means is, let's say that I have a cup of hot cocoa, and it's well, let's just draw a cup of hot cocoa here. So here I have a mug, and I have a mug handle, and this is hot, and of course there's steam coming off of it, and the temperature inside the cup is very high compared to the low temperature air that's surrounding the mug. What this principle is saying, all right, it will always flow from a hot object to a cool object, means that if you let the cup sit here, it will give some of its heat out into the air, and then after a while, the cup will have a slightly cooler temp than it did before. While the room will get a slightly higher temp. You will never see, if you set a cup of hot cocoa in a room, you will never see the room get colder by transferring whatever heat it has into the cup of hot chocolate and making the hot chocolate hotter. You just simply will not observe that. And so, what this means is that heat will flow from a hot object to a cool object. Okay? Alright, so now let's do an example with the specific heat capacity. And in your book, we'll just do an example with water real quickly. Your book gives the specific heat capacity of water as 1.0, and this is in calories per gram per degree Celsius. Right? And by the way, I should have mentioned that before, the calorie is the unit of heat. We use the calorie as the unit of heat. Okay, it's related to the joule. It's still a value of energy, but for historical reasons, we keep the unit of calorie around. Okay, so let's imagine that I have a mass of 1 kilogram of water, and its initial temperature is at 20 degrees Celsius. And I want to know how much heat is going to be needed to raise it to a temperature of 30 degrees Celsius. Okay? So, how do I set this up? Well, we're given the specific heat, we're given the mass, and we're given our two temperatures. So all we have to do is plug into the equation that we've been given, Q equals mc delta T, where delta T is our final temperature minus our initial temperature. So our mass is going to be 1.0 kilograms times our specific heat capacity. And since our specific heat capacity is in 1.0 calories per gram, not kilogram, times degree Celsius, let's go ahead and change this to 1,000 grams so that our units will be consistent. And our temperature difference, well, remember this was going to be 30 and this was going to be 20, so the temperature change is a 10 degree change in degrees Celsius. And so when we plug in all of these numbers into our calculator, 1,000 times 10 is going to be 10,000. 10,000 times 1, we need 10,000 calories to raise 1 kilogram of water by 10 degrees. Now let's kind of turn this on its head and see what the final temperature would be of a given amount of water if we know how much heat we've given to it. So let's assume that the mass is again 1,000 kilograms, or I'm sorry, 1,000 grams, and the specific heat, of course, hasn't changed. And our the amount of heat we've added this time is going to be 5,000 calories, and our initial temperature is 50 degrees Celsius. Right, so a bit on the warm side. This is something like, Not quite a terribly hot bathtub, but it might be something like a probably warmer than a warm swimming pool on a warm day. Would be something about 50 degrees Celsius. And I want to know what the final temperature is going to be. Okay, so we start out with our equation, Q equals mc delta T. And this time I need to write out Tf minus Ti. Okay, and I need to solve for Tf. So to do so, I need to divide both sides because this parentheses is an order of operation. I'm going to need to undo it last, and so I need to undo this multiplication first. So I'm going to get Tf minus Ti is equal to Q over MC, and then Tf is going to equal Q over MC plus Ti. Alright, so now I can plug in all my variables, and Q is going to be my 50,000 calories. MC is going to be 1,000 times 1. So we're going to get Q is equal to MC plus Ti. So Q is 5,000 calories. M was 1,000 grams. And C was 1.0 calories per gram per degree Celsius. And this is going to give plus 50 degrees Celsius. So my calories and my calories are going to cancel. My grams and my grams are going to cancel. I'm going to be left with 1 over degrees Celsius. Or I'm sorry, 1 over degrees Celsius, which will just turn into degrees Celsius, which is the same as this term. So I'll have degrees Celsius here and degrees Celsius here, so I can add them up. And 5,000 divided by 1,000 is 5. 5 divided by 1 is 5. So I'm going to get 5 degrees Celsius plus 50 degrees Celsius. So my final temperature is going to be 55 degrees Celsius. So by adding 5,000 calories of heat, I'm going to get a final temperature of 55 degrees Celsius. Now, word of caution, okay? My final temperature does not always have to be greater than my initial temperature, okay? And in that case, I'm going to get a negative sign with my Q, and that means that heat is being subtracted from the system. So if I were to come back and do some sort of similar analysis and look at the hot chocolate and look at how much heat had been lost, then the final temperature of the hot chocolate will be less than the initial temperature of the hot chocolate. And in this case, heat will have been lost from the hot chocolate but given to the room. Okay? Alright, so that's it for temperature, heat, and heat capacity. And in the next video, we will look at the first law of thermodynamics and the ideal gas law. We'll see you then.